Hey, I'm Rob Witcher, and I'm here to help you pass the cISSP exam. We're going to go through a review of the major topics related to cryptography in Domain 3, to understand how they interrelate and to guide your studies. This is the 6th of 9 videos for Domain 3. I've included links to the other MindMap videos in the description below. Alright, it's finally time for a seriously fun MindMap video on cryptography. No, seriously, cryptography is super cool and fascinating. It's amazing the number of services and capabilities that cryptography enables that we use every single day and probably don't even realize it. Want to purchase something online and not have your credit card details and personal information stolen by some sketchy character on the internet? Cryptography. Want to know if the update you just downloaded for your iPhone actually came from Apple and that it wasn't modified in transit? Cryptography. Are you a criminal and you want to hide your communications from law enforcement? Cryptography has you covered. Are you a large corporation that sells movies and music online and you want to protect your content with digital rights management and massively irritate your customers? Cryptography could do that for you. Secure electronic voting, digitally signing documents, defensible data destruction in the cloud, cryptocurrencies, all of them, you guessed it, rely on cryptography. So let's begin our whirlwind tour of cryptography by talking about the 5 major services that cryptography provides. First up, confidentiality, which allows us to make data available to only those that are authorized to view it. Confidentiality helps us to prevent unauthorized disclosure of information. Integrity ensures that information has not been manipulated or changed by unauthorized individuals. Integrity helps us prevent unauthorized or unexpected changes to data. And to achieve integrity, we use hashing. So equate those two in your mind. Hashing equals integrity. Integrity equals hashing. Authenticity means we can confirm who something came from. We can, for instance, verify that a message came from a particular sender. Non-repudiation prevents someone from denying prior actions, denying something happened. There are 2 flavors of non-repudiation. Non-repudiation of origin means that the sender cannot deny that they sent a specific message. They cannot deny the exact message originated from them. And non-repudiation of delivery means the receiver cannot deny that they received a specific message. And finally, cryptography enables a form of access control. By controlling who we give ciphertext to and who we give the encryption key to, we can control who can decrypt and therefore access some data. Now, let's talk about some important cryptographic terminology. And we'll start with plaintext or clear text, which is simply data that is readable by anyone. It is plain text. To protect plain text and provide, say, confidentiality, we can encrypt the data. Encryption is the process of turning plain text into ciphertext using a cryptographic algorithm and a crypto variable. What then is a crypto variable, more commonly referred to as a key? A crypto variable is a string of bits that must be kept secret. This string of bits essentially programs the cryptographic algorithm. The key determines the specific steps that the cryptographic algorithm will perform to encrypt or decrypt to transform plaintext into ciphertext encryption or ciphertext back into plaintext decryption. And that then is the definition of decryption, turning ciphertext back into plaintext using a cryptographic algorithm and a key. And here's a diagram showing the terminology we just discussed. Key clustering is where 2 different keys generate the same ciphertext from the same plaintext. This is something that we definitely want to avoid, and good cryptographic algorithms are designed to minimize or ideally eliminate key clustering. Key clustering is bad because if 2 keys will decrypt the same ciphertext, then suddenly it makes it twice as easy to perform a brute force attack. The work factor is an estimated amount of time or effort required by an attacker to break a crypto system. The higher the work factor, the more secure the crypto system. An initialization vector or a nonce is a random number that is used along with the key and fed into a cryptographic algorithm when encrypting some plain text. IVs should only be used once in any session and are meant to help prevent patterns in the ciphertext that is generated. You can feed the same plaintext into a cryptographic algorithm and use the same key, and so long as you use a different initialization vector, then it avoids producing the same ciphertext and thus avoids patterns. Good cryptographic algorithms should demonstrate a couple of properties. The first is confusion, which is focused on hiding the relationship between the key and the resultant ciphertext. The confusion property means that if one bit of the key is changed, then about half of the bits in the ciphertext should change. Diffusion is the same idea but focused on the plaintext. If a single bit of the plaintext is changed, then about half of the bits in the ciphertext should change. The confusion property is all about hiding the relationship between the plaintext and the ciphertext. To determine the security of an algorithm, we can look at the Avalanche Effect. The Avalanche Effect looks at the degree of confusion and diffusion that an algorithm provides. The ideal case is that a single bit's change to either the key, confusion, or the plaintext, diffusion, will result in at least a 50% change in the ciphertext. Okay, now that we have some basic understanding of the services that cryptography can provide and some terminology under our belts, let's get into how we can write secrets and hide our messages. The first two methods that we can use simply hide plaintext so that it cannot be easily seen or recognized and thus cannot be easily read. Steganography is the technique of hiding secret data within an ordinary non-secret file to avoid detection. For example, hiding plaintext within a picture file like a JPEG image. A null cipher is where a secret message is hidden in plain sight by mixing the characters of the secret message in with the non-ciphertext plain message. For example, the secret message could be the first letter of each word in a paragraph. Here's an example of a simple and politically charged null cipher. Let me know in the comments if you see the message hidden in this resignation letter. Okay, now let's move on to using machines and/or algorithms which encrypt plain text and turn it into ciphertext. There are two ways that we can go about scrambling the letters and turning plain text into ciphertext: one-way encryption and two-way encryption. One-way encryption means that we turn plain text into ciphertext, but then we cannot go back in the other direction. We can't determine what the plain text was from the ciphertext. Why would we ever want to do such a thing? We use one-way encryption for integrity. And we typically call this hashing. Hashing uses one-way mathematical functions which transform an arbitrary length input to a fixed length output, a fixed length message digest. Hashing algorithms need to be deterministic, which means the same input will always result in the same output, the same digest. This is how we use hashing for integrity. If you hash the same file over and over and over again, you will always get the same message digest. But if even a single bit in a massive file is changed, then the message digest will be completely different. By hashing a file at different times and comparing the hash values, you can easily see if a file has changed. Integrity. Hashing algorithms that you should be able to recognize as hashing algorithms include MD5, SHA-1, SHA-2, and SHA-3. Now, let's talk about two-way encryption, which means we can encrypt some plain text with a key, turning it into ciphertext, and then, as long as you have the right key, we can decrypt the ciphertext, turning it back into plain text. We can encrypt and then later decrypt. We can go in both directions, two-way. There are two major types of algorithms that we can use to perform two-way encryption: symmetric algorithms and asymmetric algorithms. The major difference between the two is the number of keys needed to encrypt and decrypt. Symmetric algorithms use just one key to encrypt and the same key to decrypt. Asymmetric algorithms use a key pair, two keys. Whichever key encrypts, the only other key that will decrypt is the other key in the key pair. More on asymmetric in a bit. Symmetric algorithms can be orders of magnitude faster than asymmetric algorithms. So, whenever you need to encrypt lots of data and encrypt it quickly and efficiently, you need to use symmetric algorithms. So symmetric algorithms are relatively fast, efficient, and strong, but they have a couple of huge downsides: key distribution and scalability. We'll start with key distribution. Symmetric cryptography uses the same key to encrypt and the same key to decrypt, which means that if you want to send someone some data securely, you need to encrypt it and send the ciphertext to someone and the key they need to decrypt it. I think you can see the problem here. Anyone could intercept the message and get the ciphertext and the key necessary to decrypt it. To solve this key distribution problem, you could send the key out of band, which is often not convenient or efficient. Or you can use hybrid cryptography, which we'll talk about when we get to asymmetric cryptography. The other problem is scalability. If you want to talk to one other person securely, you need just one key. 2 other people, you need 3 keys. 3 other people, 6 keys. 4 other people, 10 keys. The formula is n times n minus 1 divided by 2. And the problem is the number of keys grows exponentially. At only 1,000 other people, you need over 500,000 keys. Not awesome. Delving deeper into symmetric algorithms, there are 2 major types of symmetric algorithms: block ciphers and stream ciphers. Block ciphers encrypt or decrypt blocks of data at once, 16 bits of data, 32, 64, or 128-bit blocks. Here are the major symmetric block ciphers that you need to know about. And the top 3, DES, triple DES, and AES, you need to know some specifics about. DES, the data encryption standard, uses 56-bit keys and 64-bit blocks, and does 16 rounds of substitution and transposition. A 56-bit key is nowhere near good enough anymore, as 56-bit keys can be easily brute forced, so DES should not be used. Triple DES is using the DES algorithm 3 times, and essentially using 3 56-bit keys, although there are various ways triple DES can be configured, which is beyond the scope of the exam. This gives triple DES a key length of 168 bits, 3 times 56. However, due to an attack known as the meet in the middle attack, the effective key length of DES is only 112 bits. When the US government saw that DES was becoming obsolete, they ran a competition to find a replacement, and the winner was an algorithm called Rijndael. Rijndael was subsequently renamed to AES, the Advanced Encryption Standard. AES is an excellent and pervasively used encryption algorithm. It has a variable key length, which can be 128 bits, 192, or 256 bits, and it uses 128-bit blocks. You should be able to recognize the rest of these algorithms as symmetric block ciphers: Cast128, Safer, Twofish, Blowfish, RC5, and RC6. All those algorithms, including DES and triple DES, are block ciphers. And there are different block modes, different ways of encrypting blocks of plaintext or decrypting blocks of ciphertext. The various block modes have advantages and disadvantages. There are 2 block modes that you need to know some specifics about: ECB and CTR. ECB, Electronic Codebook, is the least secure of the block modes because it does not use an initialization vector. It is also the fastest because of this. Therefore, ECB should only be used for very short bits of random text that do not repeat. CTR, Counter Mode, is considered the best balance of speed and security. It's not the most secure, and it's slower than ECB, but it's the best compromise of speed and security. The other 3 block modes have a big advantage over ECB. They all use an initialization vector, so they are all much more secure than ECB. Taking a step back, we talked about how there are 2 major types of symmetric algorithms: block ciphers and stream ciphers. We'll now talk about stream ciphers. In stream ciphers, a single bit of plaintext is combined with a single bit from a pseudo-random cipher digit stream, a key stream, using exclusive OR math to produce a single bit of ciphertext. That's a mouthful. Here's a picture of how this works, and I think this is a good example of how a picture is worth 1,000 words. The only major stream cipher algorithm that you need to know about is RC4. If you get any questions about symmetric stream ciphers, think RC4. Okay, now an even bigger step back. We talked about how there are 2 major types of algorithms that we can use to perform two-way encryption: symmetric algorithms and asymmetric algorithms. Let's venture into asymmetric algorithms now. The major, seriously cool, and useful characteristic of asymmetric algorithms is that they use a mathematically related key pair, 2 keys. We give the 2 keys in the key pair special names and treat them accordingly. We call one of the keys the private key, which must be kept absolutely private, and not shared with anyone, ever, under any circumstances. And the other key, in the key pair, we call the public key, and we give it to anyone and everyone. Having this mathematically related key pair enables us to do some seriously useful things. Asymmetric cryptography solves the two major issues discussed related to symmetric cryptography, key distribution and scalability. We can use asymmetric cryptography to securely and efficiently distribute symmetric keys, solving the key distribution problem. And the number of asymmetric keys we need only grows linearly and not exponentially, solving the scalability problem. Not only that, but asymmetric cryptography also enables digital signatures, digital certificates, and the whole root of trust. More on all that in the next video. Now, it's not all sunshine, rainbows, and butterflies with asymmetric cryptography. It has a major downside. It is slow, like really slow. It can be orders of magnitude slower than symmetric cryptography. So, whenever we need to encrypt a lot of data, or we need to encrypt fast and efficiently, we need to use symmetric cryptography. There are a few different hard math problems that asymmetric cryptography algorithms rely on. One of those hard math problems is factoring. It is very easy to multiply two large prime numbers together and very hard to go backwards and factor the two original prime numbers. The only asymmetric algorithm that you need to know about that relies on factoring as the hard math problem is RSA. The next hard math problem is discrete logs. It is easy to exponentiate and again much more difficult to go backwards and find the original integers. There are a few asymmetric algorithms that rely on discrete logs as the hard math problem that you need to know about. The Diffie-Hellman key exchange protocol is used to securely exchange symmetric cryptographic keys over an insecure channel, for example, the internet. Elliptic curve cryptography can provide the same strength encryption as RSA, but with a much shorter key. Thus, ECC is more efficient. And that's the main thing you need to remember about it. ECC is very efficient as far as asymmetric algorithms go. Just be able to recognize El-Gamal as an asymmetric algorithm which uses discrete logs as the hard math problem. And last but not least, DSA, the digital signature algorithm, as the name implies, is used for creating digital signatures. A final bit on the hard math problems used in asymmetric cryptography. There is another hard math problem that you may have heard of that is intentionally not on this mind map, knapsack. Significant issues have been found with using the knapsack problem as the hard math problem, and any algorithms based on it should also not be used. An extremely useful tool that asymmetric cryptography enables are digital certificates, which allow us to verify the owner of a public key, and digital signatures, which provide integrity, authenticity, and non-repudiation of both origin and delivery. We'll delve into much more detail on digital certificates and digital signatures in the next video. How do cryptographic algorithms convert plaintext into ciphertext? There are two major and quite simple methods, substitution and transposition. Substitution is simply substituting, replacing one character with another. So substituting a C for a D, an A for an O, and a T for a G, and suddenly a cat has turned into a dog. One of the earliest known examples of a substitution cipher is the Caesar cipher, aptly named after its inventor, Julius Caesar. In the Caesar cipher, letters are substituted for letters 3 places to the right in the alphabet. Here's what that looks like. Notice the alphabet that is being used for substitution has been shifted to the right by 3 characters, a G for a J, a U for an X, and so on. The Caesar cipher is an example of a monoalphabetic substitution cipher. Monoalphabetic ciphers use just one alphabet for substitution. There is a fixed substitution replacement structure where if a B is replaced by an X, it will always be replaced by an X. This leads to patterns, and patterns must always be avoided in cryptography. To combat patterns using substitution ciphers, we can use polyalphabetic substitution ciphers, which use multiple substitution alphabets and thus reduce patterns. Here's what a simple polyalphabetic substitution cipher looks like using the key 4312. You can see the 2 B's in the plaintext get encrypted into 2 different letters, A and Z, in the ciphertext. A running key cipher is a substitution cipher in which text, typically from a book, is used to provide a very long key stream. to draw substituted letters from. And finally, one-time pads. A one-time pre-shared key is required, basically a really long string of truly random characters that is at least as long as the text to be encrypted. Each character of the message, the plaintext, is encrypted by combining it with the corresponding character from the one-time pad using modular addition. When done properly, using a truly random one-time pad and never reusing it, it provides unbreakable encryption. The other major way we can convert plaintext into ciphertext is using transposition, which is simply rearranging all the letters in the plaintext. Like this. A Spartan Scytale is one of the earliest known examples of a transposition cipher. You would take a stick of wood with a very precise diameter and wrap a thin piece of leather around the stick and then write your message across the piece of leather. When you unwrapped the strip of leather, your letters would be transposed and your message encrypted. The receiver would have to wrap the strip of leather around the exact same diameter stick to decrypt the message. It worked great back in ancient Greece. It also helped that a lot less people could read. Another method of transposing letters is known as rail fence or ZigZag. The plain text is written in a zigzag pattern in a table. Then the letters are copied out row by row, thus transposing them. And boom, that is an introductory mind map on cryptography. In the next video, we'll delve more deeply into digital certificates, digital signatures, PKIs, and key management. And then the video after that, we'll talk about cryptanalysis and how we try and break all this cryptography. If you found this video helpful, you can hit the thumbs up button. And if you want to be notified when we release additional videos in this mind map series, then please subscribe and hit the bell icon to get notifications. I'll provide links to the other mind map videos in the description below. Thanks very much for watching, and all the best in your studies.